For most of transportation history, wheels offered zero shock absorption. A solid wooden carriage wheel transferred every jolt of the terrain directly to the vehicle and its passengers. Engineers spent decades trying to introduce flexibility into unyielding materials, hammering intricate spring patterns into rigid metal spokes just to slightly soften the violent ride. The invention of the air-filled pneumatic tire in the 20th century solved this problem. An inflated layer of rubber could easily absorb the bumps and bite deeply into mud to provide serious traction. But rubber on its own is incredibly weak. An unreinforced rubber balloon would instantly shred against asphalt under the friction, internal pressure, and sheer weight of a heavy vehicle. Surviving these forces requires a meticulous assembly of 15 distinct components, a high-performance architectural composite. The manufacturing process traces back to the forest, starting with the raw, liquid latex drained directly from tapped rubber trees. Inside the factory, giant blenders crush this natural sap together with synthetic rubber, chemical additives, and a black carbon pigment under immense heat and pressure. This mixture produces a warm, gummy rubber dough. It is highly viscous, yet so structurally deficient that it stretches and tears under its unsupported weight. The physical assembly begins at the innermost layer with a specialized, purely airtight formulation of rubber designed to act as an inner tube. Because the rubber is weak, it needs a skeleton. A machine called a calander rolls out unyielding polyester fabric, pressing warm rubber paste deeply into both sides of the woven grid. This physical intrusion encapsulates the threads, creating a reinforced composite ply that gives the tire the load-bearing rigidity pure rubber lacks. Machinery then spins numerous cotton cords simultaneously onto this warm ply, laying them down at a very specific angle. These parallel cords act as microscopic vents. They create pathways for trapped air to escape during the compression of the later manufacturing stages. These foundational layers build a strong, airtight inner body. But this flexible skeleton has no inherent way to securely grip a rigid metal wheel rim without slipping. To lock the tire in place, the factory constructs a heavy-duty anchor called the bead, engineered to withstand intense centripetal forces at highway speeds. Equipment uncoils dozens of steel cables, grouping them tightly into precise circular configurations before completely encasing them in rigid rubber to form unyielding hoops. Small automated rollers then fold the sidewalls of the inner fabric skeleton completely over these steel anchors, locking the foundation together permanently. The external armor that actually meets the road is assembled separately. It begins with thick strips of rubber embedded with highly rigid parallel steel cords. A computerized system winds narrow strips of rubber ply directly over this steel layer, dialing in exact amounts of mechanical tension to create a graduated structural effect across the tire's surface. To create the final tread, heavy extruders push 3 completely different rubber formulations through a single die, squeezing them together into one solid profile. Paint rollers apply continuous colored stripes along this extruded strip. It's a vital visual coding system to track precise chemical recipes during complex factory processing. With both halves prepared, a massive transfer ring physically joins the heavy outer armor directed over the inner fabric skeleton. A blast of compressed air inflates the core, forcing these sticky layers to adhere together into a smooth, treadless cylinder known as a green tire. While it now looks geometrically correct, its chemical state is entirely unresolved. It remains uncured, weak, and sticky, a liability that would melt away under the friction of driving. To seal these components together, the green tire is clamped inside a massive industrial mold that operates much like a heavy waffle iron. As the metal jaws close tight, an internal bladder fills with hot, pressurized steam, expanding violently against the inside of the tire. This immense outward force presses the pliable exterior rubber deeply into the steel walls, carving the precise grooves of a summer tread pattern into the surface. The extreme heat and pressure trigger vulcanization. At the molecular level, individual polymer chains snap together, forming strong cross-linked bonds. This strips the rubber's sticky properties and dissolves the boundaries between layers. The 15 components cure together into a single, hyper-elastic solid. Workers trim away any excess rubber flash, and the tire passes through rigid geometric inspections to ensure perfect physical uniformity. The finished object is a chemically fused, highly engineered composite structure, carefully built to absorb, grip, and survive the brutal physics of the open road.